Right, so let's see. So today will be the second last class. So we still have the makeup class, so please make sure. There's a survey, I just sent it out this morning. I'll send you some reminders, so please just go there. And if you're interested in attending the makeup lecture and also the exam review session separate, right? There will be 2 sessions in total. So please go to the e-class and then just indicate your preference. But my impression was you guys might prefer that Wednesday, maybe around 11 a.m., if I'm still right? Okay, so anyway, we'll see how people actually turn out to prefer. So please do fill it out because I think you guys really come to the class more often in person, so please fill it out. Okay, any questions? Yes?
Is the makeup lecture the one that you're asking for? Is that
Actually both. So basically those are the times I can make myself available. So once you guys indicate preference, I can choose maybe the most popular 2. One will be makeup lecture, we'll do that first, and then the one that's a little bit closer to your exam, we can make a review, right? We can give you some benefit because you might get more questions accumulated towards the end, right? Yeah. So there'll be 2 sessions for sure, yeah. Yeah, so once we decide the time, I'm gonna reserve the room and then we'll be good. Okay, good. Okay, so let's do a quick recap and then there's one more little stuff I want to speak about for topological sort and then we can move on to a new topic today. Okay, minimum spanning tree is a very exciting topic. We can definitely talk about half of the story, and then we'll do the other half in the review session. Okay, it's really worth our time discussing it. All right, so last time we actually spoke about 2 things. One is something called DAG, directed acyclic graph, and the other one is topological sort. So what would be the motivating scenario? So whenever you got some application to build, and there is certain like a dependency amount objects, then that might be the situation you want to build some DAG, directed acyclic graph. So every arrow over here signals some dependency you have to somehow represent in your application. So a typical example would be if you say one course must be taken before another course, it's dependency. So generally think about dependency. And then we talk about something called topological order. So basically, given a graph which is non-linear, you can somehow linearize it or sequentialize it into a sequence, like an array or sequence of vertices. And we talk about how you can actually double check to see if a topological order is legitimate with respect to some DAG over here. So the way to check it would be, you want to take every pair of vertices, or this pair, and etc. All the combination of pairs of vertices, if, for example, there is a direct edge between the 2 vertices. In this case, these 2 vertices will be these 2. There is a direct edge. In that case, this origin must come before the destination in the topological order. So if I give you any order there, I want you to justify to me whether or not it's a legitimate topological order with respect to some DAG. You should be able to do it, right? It should be a simple one for you to decide, okay? Questions about this? Okay, that was not too bad to grasp. And then the weight, given some input DAG, we want to generate some topological order. That's something called topological sort, right? We talk about how to trace it and also the pseudocode. Let's do a very quick recap. So that's the algorithm. You can think about topological sort is more like a very slight extension to the depth search, basically. Okay, you can definitely look at the Java code. And you can even try it out if you want to, just extend your assignment number 1 and try to use the depth first search there and create a new method, right? That's something I'll leave to you, okay? So since it's actually based on the depth first search, so it turns out every vertex is going to be visited, is going to be pushed and popped exactly once to and off the stack. And also, every edge is also going to be visited just once. We never try to look at the same edge twice. That's why we can mark it as discovery edge or back edge, right? So the running time is going to be it's going to be proportional to the number of vertices plus the number of edges. So in general, if you're trying to adapt your algorithm from the depth first search, if the extension is not very computationally expensive, you can expect the running time to be n plus n. That's the principle. You can think about it, or you can even ask me later, maybe in the review session, okay? All right, and then we did some example here about topological sort. So in principle, it really depends on what will be the starting vertex you choose to do the depth first search. So in the particular example we actually first of all chose E over here. So by doing a topological sort on that, you're only going to cover the vertices reachable from E. That's not going to cover the whole graph. And then you're going to do another second iteration of the topological sort. That one is going to cover this part over here. And the final one is going to cover over here. So it really depends on which vertex you choose. Visually, you can definitely choose the one that's going to reach out to the most vertices. It's going to be efficient. But when you're implementing an algorithm, you just don't know. So it really depends on which one you happen to choose. Okay? So every individual iteration is going to generate some sequence. You're just going to keep accumulating them into the list. Okay, just make sure you know how to trace the topological sort. And this, I believe there's another example there for you to try it out. Okay, slightly more complicated, right? Give it a try on the topological sort. You can try to say maybe the first iteration we're going to start with here. The second iteration start from here. The third iteration start from here. And the fourth and the fifth, right? You might just got different iteration of topological sort. And finally, you should still get an order. Another very important characteristic to remember. Whenever you're trying to get given a deck, the number of topological order that are legitimate may not be just one. It could be multiple. So that's something you will also see on the slides. So it's not really like a unique order you can always generate. It might be multiple ones that are they're all acceptable. All right. And then I think that's the last example we talked about. It's a very practical example. So given some specification about how the variables are being related in the post states and also the pre states, right? Things like that. We have such specification. We want to sequentialize or linearize the variable assignments. So the ultimate variable assignment we got is this. This is like a linearized order. We can simply execute line by line, right? Sequentially, okay? How do we go from here into something like this? Step number one, based on this, you're going to build some dependency graph using the deck. And from there, we're going to do a topological sort, which will be something over here. So once you get the topological sort, you got some topological order right here. So that will be the order of variable assignments. So that's what we did last time. Okay, so maybe take a look at the recording if you need to catch up with some details. Okay. Any questions about this example here? Okay. So I would say, let's say during the exam, right? So I might give you a different problem over there, which might also require building the deck and also performing a topological sort. How do you tell? It should be the problem to apply topological sort. I would say any problem that kind of suggests there are dependencies among objects. That would mean you may want to build a deck and do topological sorts. Dependency is really the key word to give you some hints. Okay. All right, guys, question? All good? Okay. Let's now just do one more thing to clarify topological sort. Okay. So we said that it's basically about doing some extended depth first search, and then you can do topological sort. And now the general question is, can I simply just do a breadth first search and then expect some sort of a result that's also legitimate for topological order? The answer should be no. Okay. There is some algorithm that will actually involve some very major modification for the breadth first search that can make topological sort work, but that's not what I'm talking about. I'm saying just perform a very pure breadth first search, but it's not going to give you the order you're expecting. So let's now take a look at some simple example, and then we'll see. Okay. So let's say we got this graph over here. And also in the exam, also do expect sometimes I may not give you the visual of the graph right away. You may want to look at the textual description for the graph and then build some graph first yourself. All right. So hopefully it's not too bad, right? You can see we got 3 vertices, S, A, and B. And these are the edges, 1, 2, and 3. So 3 vertices and 3 edges. And of course, if the graph is weighted, I will also give you the weights for the edges. All right. So assuming that you know how to build this, let's just now build together. Right. So the graph will look something like this. So we have S, and then we got A over here, and also we got B. S, A, and B. And we got 3 edges. S to A is directed, and also S to B and also B to A. Okay, so that's a simple graph that we can build right here. Oh, actually, it can make it draw a little bit better. There we go. All right, so that's a graph. Let me make a copy. And this graph is completely legitimate for a DAG. So you can, as you can see, it's directed, it's also acyclic. So it's a legitimate DAG. So you can see right away, it's a legal DAG. If there's a DAG, we can perform topological sort. That's what we can do. Okay, let's just revisit very quickly about how we can do topological sort using a variance of the depth search. Okay, so let me start with the depth search, which will be, let's say here. Let's say I want to perform depth search and the topological sort. Okay, that's something we discussed last time. Let's just do it again. Okay. So of course, we're going to record the list of pushes and also pop. Okay? And in both cases, let's assume we start with source vertex S. Let's say that's what we start with. All right, so and then we got our stack over here. Okay, so to start with, we're going to push S in there. And then let's assume that we're going to visit the incident edges in the alphabetic order. Okay? So the first one we're going to visit will be 1 here. We're going to visit A. A should be pushed. Right? And as far as A is concerned, there's no more outgoing edges. So A should be popped. Right? So A should be popped. So we go back to S. You can see S over here is now going to another incident edge. So that'd be number 2, right? So we're gonna push B to the stack and B to the stack. So now for B over here, of course we may go over here, but you know, that's a back edge. So that'd be number 3. Okay, so after this, B is completely gone. I mean, all the outgoing edges are handled. So B can be removed. So B is gone. And then for S over here, now both incident edges have been marked. So now we can also pop it out. So it's S. And the reverse order of the pop is going to be the topological order. Okay, so you can think about right here, it's going to be S followed by B followed by A. So this will be the topological order. Topological order. Okay, some very important insights about depth search, right? So you can think about over here, for example, let's say A here. When we try to pop A from the stack, we can only do that when all the edges going out from A have been already marked. So that means there's nothing else that depends on A that have not been handled. All right? This is a very important insight. Okay. So here, when A is popped out, all outgoing edges of A have been handled. Okay? Or put another way, anything that A depends on have been handled. Have been handled. And similarly, when we actually try to do B over here, B depends on A. But now when we try to remove B from the stack, it's guaranteed because B over here, we know that A has been already handled in that particular order. So now when we go to the B, we can now also pop it out. And only after A and B have been handled can we actually go for S over here. So that's certain order we have to follow, the dependency. So depth search naturally is a very good way to really let us figure out the dependency, to linearize the dependency. Okay, so that's about depth search. Okay, and think about this insight over here. Okay, So that I think that one's also a very important insight for us to remind. Okay, happy handled. All right, let's take a look at the same graph. If we try to do breadth-first search, it's a very simple example, right? So by that one there, you can already kind of see the order we're going to get between A and B is not really based on the dependency or outgoing edges. It depends on something else, which nothing to do with dependency. Okay, so let's see. All right, so what we have is, let's say we got InQ and DQ, right? We got InQ, and also we got DQ, these two. And over here, let's talk about, we just do breadth-first search. What we want to see is, by just doing a breadth-first search, we can observe that it's not straightforward to get a topological order right away. That's the main thing to catch, okay? Okay, so we can start with S, like the breadth-first search case. So we're going to InQ S, okay? And then we're going to go for the incident edges alphabetically. So we're going to InQ 1 and then 2. So we're going to go for A, and then we go for B. Okay? So far, you can see that it's really the same, A and B. However, the way we DQ, right? So here, when we, as soon as S is actually, we have already added all the incident, all the outgoing edges for S, we can now DQ it, right? So now S is gone, all right? And then what about A and B? So now the order for us to really DQ A and B, according to breadth-first search, really depends on the order they were added. Nothing to do with whether this is an outgoing edge between B and A. Not really, right? That's something very important to see, okay? So now it's simply going to be A followed by B for the DQ. And it's very important to point out here, this order over here. This order does not consider the fact that B depends on A. Right? You can see there is some edge right here, but that one is not even considered because the order in which A and B will be in DQ just correspond to the order they are InQ'd, right? That's a breadth-first search, just first in, first out. Okay. Does not. Okay, so that means it's not suitable. Not suitable for generating topological order. All right, so that's the second insight to make. All right, question about this? So, well, depends on how you phrase it, right? So I'm just using the phrase that. So when I say B has to, well, it depends on the application. How about that? You can say, okay, B must happen before A. That might be the most precise way to say that, right? If you say B must happen before A, depends on the situation. Sometimes you can say A really depends on B, but in some other situation, B can depend on A. So maybe the best way, maybe the most accurate I should have said would be B must happen before A. But this arrow here was not even considered when I try to DQ A and B, right? Yeah, that's my main point. Yeah, good. Okay. Okay, how about this? I think that's a good point. I think you're confused for fairway. Okay, B depends on A. So I really meant to say B happens before A. Okay, good. All right, so now we're done with the topological sort. Any questions? All good? Okay, let's now talk about new topic. Okay, also still about graph. So what we'll do is we're going to talk about we talked about spanning tree before, and there's some notion about minimum spanning tree. I'm going to talk about it just to clarify what it really means, and then we're going to see there is a design method for figuring out or constructing minimum spanning tree called the greedy method. You may have heard about greedy algorithm, so we're gonna do that today. And so today, just about give you some annotation, just understand the structure for greedy algorithm. We actually have already learned about greedy algorithm so far in the course. The Dijkstra algorithm is actually greedy, but we're going to see exactly how that one, and also the one we're going to talk about today for minimum spanning tree, both instantiate some general structure for greedy method. We're going to talk about it. So later on, if you want to design greedy algorithm yourself, just make sure you also follow that kind of a structure. Okay? And then we'll do one example to really trace. The algorithm itself is actually incredibly simple to really trace, just a little bit tedious, but we're going to do that as well. And then that'll be it for today. And then when we come back for the makeup lecture, maybe next week, so I'm going to just dive a little bit deeper into some property about the greedy method. Okay, something we'll do maybe next time. Today, just focus on something, at least we can operate on the algorithm. Okay. And the slides you will need to look at will be, let me show to you right here. So we start from slide number 79. Okay, but I'm gonna just focus on my iPad so we can take some notes together. Okay. So first of all, let's define minimum spanning tree is a problem. So you will see the acronym MST. Okay, minimum spanning tree. Okay, so that's the problem we are solving. And whenever you talk about the minimum spanning tree problem, the input, there's some assumption. So the input over here, to start with, we assume the input is simple. Do you guys remember what a simple graph is? Without two things. Cycles and parallel edges, exactly, right? Just remember the terminology, right? It's simple, undirected, and also weighted. Okay. So now for the weighted part, let's now clarify something as well. Depending on the application you're trying to design the algorithm for. So when you talk about the weights for the edges, the weight may have two possible meanings depending on the application, right? The weight itself may either mean something associated with a cost, in which case you want to minimize the cost, right? It makes sense. You want to make sure the spanning tree that you eventually got has the minimum cost. Or it could be that the weights actually indicates or represents some kind of benefits, or like a score. In which case, you would like to maximize the cost, maximize the weights, basically, right? It really depends. But for us, we're going to focus more on the minimum over there, okay? So sometimes you might want to calculate a spanning tree that's a maximum. That's also possible, okay? But for us, we're going to focus on just the cost and minimum, okay? And just before that, you will see that on the slides, I just gave you just two possible examples, right? Since you guys are more from the engineering, I just try to find more engineering example, right? So maybe the first one is a very typical one. If you want to build network for like a cellular tower, right? You want to reach out to as many as possible. And you want to make sure every cell tower is actually covered. And also you want to build a link with a minimum installation cost, right? And also another one is just about the chip design, okay? Over here, right? I don't really understand about chip design very much myself, but that's just one example. As long as you can somehow build vertices and also edges between the artifacts in your application, then most likely you can have a minimum spanning tree problem to solve. All right, anyway, so you can definitely find many other examples for minimum spanning tree. Okay. And the one we're having over here is just another one. Okay, so you can see that over here is the flight network for some airline company. So for example, between San Francisco and Boston over here, so that one there is about this much miles or kilometers. And then somehow we want to find some spanning tree that's going to be the minimum distances, right? That sounds another one, okay? So the input is going to be something like this, and the output is going to be something like that, okay? So you can see I try to so the thick green edges, all these together right here is going to form a spanning tree. That's a minimum cost. But I'm going to define the terms in a moment. Okay, that's what you will see. Okay, let's now define the terms. So let's now start with the notion about a tree. All right, do you guys remember what a tree is? Yeah, go ahead. Undirected and acyclic. You're missing one part. Connected, exactly. Good, awesome. Already done, this will be a good review, right? So the tree is undirected, acyclic, and also connected. And, okay, just also remind you about undirected and acyclic. These two together means it's a forest. All right, and then also a tree is actually just a subgraph. It's not necessarily spanning. So that's why we say spanning tree, right? So this is a subgraph. All right, so let's now go to the next one. Also, we got spanning tree. So spanning tree is basically a tree that's also a spanning subgraph at the same time. It's basically a tree, and at the same time, it's also a spanning subgraph. Does a spanning subgraph have to cover all the edges or cover all the vertices? Vertices, right? Okay, good. Yeah. Just remember that. Okay, good. And then now our problem here is about minimum spanning tree. Minimum spanning tree. Okay, so here just do a little bit of math, very simple equation. Okay, so the minimum spanning tree is going to be, so here, let me just give you the notation here. Usually when we say minimum spanning tree, we're going to use a symbol called T, like a tree. Okay, the T here is just a set of edges. Okay, we see one example here right away. Okay, right away over here. Let me just write it down just for the first time. So you can think about, for example, the minimum spanning tree for this graph over here that's given, T, will be a set of edges. Okay, so let me just write Boston to JFK, and also PVD to JFK. Okay, because there's a reason I'm numerating them. Okay, I'll show to you. JFK to BWI, and also BWI to ORD, and also BWI to Miami, and also ORD to ORD to DFW. Okay, let me just make it a little bit smaller. Almost there. Okay, and we got DFW to LAX. Finally, we got LAX, San Francisco. All right, right here. Let me just double check. 8. All right, basically all these 8 you can double check. All right, all these 8 edges. So whenever we talk about minimum spanning tree, it's just about all the edges for our notation. Okay, just all the edges that should really give you the minimum weights. So now there's one example. So that means all the weights added together should be the minimum in order for you to have a network that's going to span through all the vertices. So now we say that the weights of the spanning tree. Let's say given that T is this, you're just going to look up all the weights together. So you're going to add up this all together, right? So that one will be the sigma for all the edges, let's say U and V, that's in T, right? Every one of them. And then you simply want to calculate the weights want to add up the weights for each edge, like that. So whatever number you're going to calculate from all these is guaranteed to be the minimum, all right? Yeah, so the new notation is really about the weights of some spanning tree. And that one there should be guaranteed to be the minimum. And let's now also talk about some property we mentioned earlier when we first introduced graph. Okay, I'm going to write it down here. Okay, so we know that the number of vertices is 1, 2, 3, 4, 5, 6, 7, 8, 9. And we know that the graph is connected, right? Graph is connected. Okay? So that will always mean for you to have a spanning tree, the number of edges in spanning tree. Do you remember there's a little formula that we actually, the property? It should be exactly equal to the number of vertices minus 1. Okay, double check, there's a property we even proved earlier, all right? It's going to be equal to the number of vertices minus 1, which will be 8. Okay, let me say that again. When you are given a graph that's also connected, guaranteed, the spanning tree is going to contain exactly the number of vertices minus 1 edges in order to be a spanning tree. Whether or not it's minimum, you have to look at the weights, okay, to add up. Okay. There's another very important implication from this, okay, which I'm going to say as well. So when you look at the 8 over here, or we'll put it more general, okay, it's going to be the number of vertices minus 1. This tells us if you want to write an iterative algorithm to really compute the minimum spanning tree, you should always keep track about how many edges you have already in the spanning tree so far. As soon as you get to n minus 1, you should stop. Because theoretically, you should get no more than n minus 1 edges. That's something we'll see. Okay? It's a very important insight into why the algorithm we're going to talk about today, they got some very peculiar condition for the while loop. Okay, so this one here, I'm going to write it down. Okay? When building a minimum spanning tree iteratively, as soon as the number of edges is equal to number of vertices minus 1, terminate the loop. Terminate. Okay, I'll read it out just in case you cannot read my writing. Okay, so I'm saying whenever you're trying to build some MST, minimum spanning tree, iteratively, as soon as the number of edges in the minimum spanning tree built so far contains exactly number of vertices minus 1 edges, you should know that you should terminate. You should not continue any further because theoretically you should not have more than, you should got exactly n minus 1 edges. Okay. Okay, question? Okay? All right, good. All right, so let's see. And before we actually go over the algorithm, let's talk about the idea about a greedy method, just in general. Okay? So in this course, ultimately, we would have covered 2 greedy algorithms. One would be the Dijkstra, the other one would be the one we're going to cover today. Okay, we'll see. So let's talk about the ingredients for greedy method. Right? I'm just going to write some points all together so you can just also, hopefully, you can also remember better. Okay, just to start with, greedy method is a design method for algorithm. Design method for algorithms. Let's have some intuition. I'll try to give you, I'll try to enumerate about the different ingredients, and then we'll see how those ingredients can be seen, can be reflected in the Dijkstra and also in the algorithm we're going to go over today. Okay? So, number one. The greedy algorithm you want to design is a step-by-step construction of some solution. Okay? It's a step-by-step or iterative construction of some complete solution. And when I say complete, another term you will hear quite often is it's going to be a globally optimal solution. Globally optimal. So for example, if the task is to construct a minimum spanning tree, we'll want to make sure the ultimate spanning tree we have is guaranteed to be the minimum in terms of the summation of all the edges weights globally, okay? Eventually, okay? So think about we are trying to construct something, okay? Okay, that's number one. And then for each iteration, there's something we can say. From each step and also the iteration. Okay? There are several things we can say. Okay, number one, there will be multiple choices we can make to make some progress. Okay? So there are multiple, they said feasible choices exist to extend. I'll visualize about extension in just one moment. Let's go over the bullet point first and I'll visualize what's going on. Extend the partial solution so far. So think about in Dijkstra. Remember we talked about the capital S, the set, right? Think about capital S start to be empty. And then we want to gradually extend the capital S set until it contains all the vertices. Right? It's more like a partial solution when you haven't really covered all the vertices, but eventually you're going to let it cover all the vertices. One vertex extension at a time. Okay, so this will be point number two. And then, okay, another one. And how do we make some progress? So among all the feasible choices, you want to choose the best one. Okay, so you want to pick the choice. So pick the choice that's the best right now. With respect to a cost or score function. Okay, so I'll talk about cost and score function a little bit later. Okay, I'll talk about this one in just one moment. Okay, so we talk about complete solution. That's something we want to build ultimately, and then for each iteration, we want to build based on what we can get so far, what we can get the best right now. The best right now. Okay, so this is like in contrast with the globally optimal that we want to build ultimately. We want to get a locally optimal first. Okay. So this one here, the best. So these are the locally optimal, which not necessarily making the solution so far the globally optimal. Okay, I'll just write down the point first, and then we'll try to go over them. Okay, locally optimal. Okay, however, not necessarily globally optimal for the whole solution. Right, we're just trying to gradually building. Right? And then the next one. Over here. Once a choice is made, you don't really have to revisit the choice. Once the choice is made, that's it. Okay? You don't have to, you cannot undo it. You never undo it. And sometimes people also say we don't really backtrack. So think about in the Dijkstra algorithm, once we remove a vertex from the priority queue, we never put it back. Right? Once it's finalized, we don't need to revisit that. Okay? That's really about this bullet point, what it is saying. Okay, almost there. 2, 3, and 4. Okay, I'll try to put all these labels in the Dijkstra algorithm in another page so you can see the correspondence. Okay, okay, let's talk briefly. So just about the cost function right here. Okay, so I'll put a star, the cost, and also score function. Okay, it's really got two purposes. It can help us rank the choices. So, for example, the capital D in Dijkstra. When there are so many vertices in the priority queue, which one should we pick? The one with the minimum D, right? So we have to pick the best choice that's currently in the queue. Okay? And also, we can also use that to measure the partial solution so far. Okay, so these are the two purposes. Let's visualize very quickly. Okay, okay, let me now try to just use a single diagram here. So greedy method. Okay, so visually, let's say we have got some solution so far, which is partial. Let's say this is what we got, partial solution so far. And now, we haven't really reached the final solution just yet. And now imagine the pink one here is the final solution we want to get to somehow. It's more like a final solution, which is strictly bigger. Final solution or complete. And now what we should do is we should somehow expand the partial solution to be one element bigger. How do we do that, right? So now the greedy method tells us whenever you're trying to expand your partial solution, you have choices. So you may have maybe choice number 1, and you got choice number 2. You might have another choices over here. For example, you may have different vertices you can choose from the priority queue, but which one should you choose, right? So there is the so-called greedy step. So for example, let's say somehow we choose this one over here, okay? So by choosing this one here, it's called a greedy step. Greedy step. That one there is gonna opt for the choice with the minimum cost. And what that would do is, it's actually going to extend the solution to include just this choice right here. So you can think about this part over here is the extended solution so far. What's important is this extended solution is still within the final solution that we're building. We're going there, not quite yet. Okay. So, final point. So over here, each greedy step guarantees that we are one step closer to constructing the complete solution. As long as you can follow the greedy step, which is choose something that's a minimum, in that way, you can guarantee at the end, once you have gone through all the steps, all the iterations, you will reach the final destination. All right? Yeah, conceptually. Okay? All right, any questions so far? Okay, so just an idea. So why don't we take a short break? After the break, I think what we should do is we'll do some very quick correspondence check just to see the greedy method in Dijkstra algorithm, and then we'll introduce this algorithm for minimum spanning tree construction, and then we'll do some tracing. All right, good. Okay, let's take a short break. All right, so before we actually try to trace the algorithm about constructing the minimum spanning tree, let's see our Dijkstra algorithm just to see how it relates the different ingredients of greedy method to Dijkstra algorithm very quickly. Okay, so when you study later, you can just see the different labels 1, 2, 3, and 4. Okay, so let's now switch to this page. Right, that's a Dijkstra algorithm. You guys are familiar. Let's now revisit that very quickly. Okay, so this indeed is a very standard, has to satisfy the very standard structure for greedy algorithm. Let's go one by one. Okay. So number one, you can start by looking at the iterative nature about constructing the solution. Okay, you can see right here. So we're basically trying to iteratively construct a solution. And if you kind of remember the way we talk about Q, right? Q is really, you want to contrast with the imaginary set S. As Q is shrinking, the imaginary set S is growing, right? Okay, so for the first point. So this is really point number one. We talk about a step-by-step construction of solution. You can think about ultimately we're going to S. And the S over here should really contain all the finalized vertices. All the finalized vertices. Okay, that's ingredient number one, Dijkstra. It's iterative. Okay, so number two. Just before that, we also got the notion about cost function. So the cost function for Dijkstra is simply the D value for V, right? Exactly what D really means, you guys should know pretty well, right? So make sure you revisit that for the exam. Okay, the cost function is D. And we choose the minimum cost, the minimum D. So now look at this line here. This one really contains a few ingredients that we can speak about. Okay? So first of all, you can see that for each iteration, when you look at the queue, the priority queue, right here, that one there really contains the feasible choices you have to grow the set S, right? But we're going to choose the minimum, right? So this will be the point number two. So you got multiple feasible choices exist to extend S, right? This S over here. And when we say choices over here, we simply got the vertices that remain in the priority queue. Okay, second one, we do have choices. But now the greedy step is going to say among all the the greedy step is going to say among all the multiple feasible choices, choose the best one right now. Choose the minimum, D. Okay. So for that one there, you can see for the minimum part, right, extracting the minimum from the heap, priority queue. So this one here is going to be number 3. Okay. So it's the greedy step. It's going to choose the minimum V with the D value. That's minimum, right? And then this part here, symmetrically. All right. This one here is also very important. Once we have removed, this will be number 4. Once vertex removed, never put it back. Never put back. Okay? No backtrack, basically. All right? So these are all the 4 ingredients we just mentioned before the break. Right? You can actually take some time to really see exactly how the Dijkstra algorithm satisfies the structure. All right, one more thing. So if you look at the details right here, just about how we can update the specific about all the incident edges that can lead to the different vertices, right, from the U that we have chosen. Okay, so this part here, just for this part. All right. So this part here, after this is done for each iteration, there's no guarantee we have really gone to the final solution just yet, but we haven't really diverted from the right path. Okay, I'll write it down. Okay. So this part over here, okay. After each greedy step, the solution is only partial. It's only partial, not the final solution just yet. However, we should be on the right track, guaranteed, as long as you follow the greedy step properly. Only partial. Okay. S is still subject to extension. Right? We might add more vertices into S. Okay. All right, so think about the Dijkstra algorithm. Okay. So we got about 23 minutes. I want to be safe. I really want to trace the whole algorithm together with you. So this is the actual algorithm for constructing the minimum spanning tree. It's called the Kruskal algorithm, just the name. Okay. That one there is incredibly straightforward to really execute. So I would say, rather than going through the detail about each line, let's just trace it directly. So after today, based on the example we traced together, in the next 22 minutes or so, you can now go back to the code and fully get it. Okay? Just one thing you got to notice. The while condition. The T, which is the minimum spanning tree we are building, we are saying that while this is still less than or equal to n minus 1. So there's a reason for that. Right? You want to make sure as soon as it's exactly larger than that, you have to make sure you exit from the loop. Right? It's very important. Okay? That's the only thing I'll mention. T should be exactly equal to V minus 1 when the graph is connected. Okay? There's a property we just mentioned when we talk about minimum spanning tree. But let's now trace the algorithm. Okay, this is a graph. It's reasonably complicated. Okay, so this graph here. Okay, let's just get something. Let's do some look ahead. The number of vertices we have is. So let's see here. So we got 1, 2, 3, 4, 5, 6, 7, 8. 8. And given that the graph is connected, guarantee the minimum spanning tree, which is a spanning tree, how many edges are we expecting? 7, right? A minus 1. Look ahead. So the T we are building is going to be exactly the number of vertices minus 1, which will be 7. So we're going to gradually build the T. As soon as we hit the T to be of cardinality or size 7, we can stop. All right, we don't need to go any further. All right. So for this particular run, there will be 9 iterations in total. Okay, let's just go ahead. Okay, maybe the first few, it will take a little bit longer to grasp. Other than that, it should be rather straightforward. Okay, let's now trace it. So let's now, first of all, talk about the iteration. So I will start with over here. So I might just get about 5 iterations here, roughly, and then I'll do the remaining 4 right here. Okay, and the second column, we're gonna choose the minimum edge weight. The minimum edge. So as opposed to, if Dijkstra, we're gonna choose the vertex with the minimum capital D value, right? It's a little bit different. So in the case of the minimum spanning tree, we are choosing edge. And in the Dijkstra algorithm, we're choosing vertex. So it's kind of different. And then, so there is something called clusters. Okay, I will show you what that really is, clusters. So think about clusters is simply sets of vertices. Okay, I'll get there. And also, the ultimate minimum spanning tree we are building is T. All right. Initialization, right? To really, before the first iteration. Okay, nothing to choose from just yet. And then we're going to have the clusters. So every vertex will be in its own cluster. Okay, so think about since we got 8 vertices, we got 8 clusters. So we got, here. So we got over here A, B, C, D, E, F, G, H. 8 clusters. So initially, all the vertices have their own clusters. We got exactly 8 clusters. And the edges will just be empty set. We haven't collected anything just yet. Start with empty. Eventually, the size of this set here is going to be exactly 7, eventually. Okay? All right, so let's now talk about it. Of course, you should also, initially, this is something I will not really I will not actually put in the table. Okay? We also put all the edges in the priority queue, and we're going to extract minimum 1 by 1. All right? All right, iteration number 1. Which edge should I pick as the minimum weight? Which edge? A, B, agree? Well, absolutely, minimum. All right, good. So that one there, the weights of A, B is equal to 1. And let me call this edge over here E1. Okay. So what we have is we are trying to collect this edge over here as the first edge in T. All right. So now the cluster. This is the most important thing. Since the edge is going from A to B, conceptually, you want to think about, if I go from A to B, am I going from one cluster into another different cluster? If I am, I'm going to merge them. Okay? A here is in this cluster. B here is in a different cluster. So that would mean I want to merge them in this iteration. So what this will do is it's going to merge A and B into a single cluster. I essentially reduce the number of clusters by 1. Eventually, I want to have a single cluster with all the vertices, eventually. All right, so just know the direction we're heading, okay? The rest doesn't change. So now we got C, D, and also E, F, G, H. And the T here should contain just E1. All right, so that's the first iteration. Okay, follow so far? So the first iteration tells us a greedy step where we chose the minimum edge with the weights, with the edge with the minimum weights. And then we try to see if we can merge two clusters together into one. All right? Second iteration. Which one should I pick? BC? Yeah, good, awesome. There we go. Okay, so this one here is going to be the weights of BC is going to be 2. And that one there, again, we're going to try to see which cluster is involving, right? So now you can see B is here, C is here. Different clusters, merge them, okay? So what we do is we do A, B, and C. And then here we got D. And am I able to just copy? Yes. The rest the same. All right, now the T here is now going to be basically containing 2 edges, E1 and E2. So E1 before, and also E2, which we just introduced. I'll call it E2 right here, okay, E2. And of course, E2 contains these 2, B and C, right? I look at B and C, they're from different clusters, so merge them. Essentially, you can think about the minimum spanning tree so far we're building is really just up to here. That one there connects A, B, and C in this cluster. That's what we're doing. Okay? Let's do one more. Okay? The iteration number 1, 2, 3 will be very standard. You can get used to it. But number 4 is going to be interesting. Okay? But let's do number 3. What should I pick? You got 2 options, right? Which is okay, right? Remember we say priority queue, it's okay to have duplicate keys. So now you got option. You can either go for AD or you can go for CD. Let's say we go for AD. Okay? Doesn't matter. Let's say we go for AD. Very good. Now this one also reminds you about the property for priority queue. Keys can be duplicated. It's absolutely okay. So let's say we choose the AD right here. Let's say. So it's going to be iteration number 3. The weights for AD is exactly equal to 2. And then we got E3. And that one there is here. Okay? And then, so here, let's see where A and D's are. A and D, A and D. Merge them. All right? So you can now merge these 2 clusters. So what we'll do is we're going to merge them. So now we got A, B, C, D. And then over here will just be the same. Right here. And then I'm just going to put one more edge to the T. So here we got basically E1, and also we got E2, and also we got E3. Okay, so far so good, right? So let's see what happened in iteration number 4. Okay. So for iteration number 4, what will be the minimum? CD, right? That's your minimum, right? Yeah, choose it, right? Just follow the greedy step. So for that one there, it's so there are two possible, almost like an if then else. There are 2 possible ways you can handle the greedy step. What we have seen so far, 1, 2, and 3, are we are merging 2 clusters. Another scenario would be we don't merge anything. But let's see why. So let's see number 4. Okay. So the weights of CD is equal to 3. Oh, I just noticed that I had a small typo over here. So I believe this one here, oh, sorry. So this one here should be actually 3. Okay. Yeah. Just in case. All right. So now we got CD here. And that one there, I'm going to just put something like this. Okay, the color convention will be when I put gray, that means it's not going to contribute to the minimum spanning tree. But let's see why. So now if I try to look at a cluster, so C and D, I got C and D. They belong to the same cluster. Nothing to merge because they are members, right? No change. No change. And here also no change. Simple iteration. So the minimum spanning tree so far remain to be this one here. All right. All right. Iteration number 5. So that one there. Let's now try number 5. Okay. What should we pick? What's the minimum? Would you agree? It's EF, right? There we go. EF, right here. All right, so here, let's now put this row over here. So the weights of EF, let's now write it down precisely. The weights of EF, which is 4. Okay, let's call this one here E number 4, because it's going to be merging. But let's see exactly how it's going to merge. So for that one there, you can see we got E and F. So we got E and F. Different cluster. Merge them, right? So what we got is, so first of all, we got A, B, C, D. Okay, let me just, okay, A, B, C, D. And also we get to merge the E and F. And then we got E and F. And over here, also we got G and H separately. And the minimum spanning tree should now contain 4 edges. So that would be E1, also E2, and also E3, and also the current one, E4. All right, so far we got 4 edges. We are basically more than halfway towards 7. Josh?
You merge in.
Oh, absolutely. Thank you. Very good catch. So that one there, yep, thank you so much. Good, all right. Now number 6. I'm actually doing better on the spacing before I compare with how I practice. That's good. So now number 6. Number 6, would you agree should be DE? Yeah? Because now you can see we have already handled all these. All that's left will be 5, 6, 7, 8, 9, and 10. Right? We're just going in increasing order, basically. Right? So now the next one will be 5. So that one there is going to be DE. Let's now use purple. Okay, DE over here. So now we have the weights of DE is equal to 5, and this one here, let's call that E5, okay? Because this one, it turns out, you can also gonna go across 2 clusters. Let's see. So we got D and E. D here, E here. All right, so now you're gonna merge the orange cluster and the pink cluster. We're gonna merge them. So what's going to happen is we're going to get A, B, C, D, E, F. A, B, C, D, E, F. And then we got G and H separately. Got G and also H. All right? And then we're just going to have one more edge to here. Okay. So we're also going to have E5. E5. So we need at least another 2 iterations to add 2 more edges, at least. Okay? Iteration number 7. Which one? Yeah, CF, right? I agree. Thank you. Yeah. But now, can you imagine? Is that going to contribute anything to the cluster? Not really. Let's see. Okay, let's be precise. So now CF. CF over here, number 6. Okay, so for that one there, is going to 7. The weights of CF will be 6. That one there, you can see we are basically trying to connect C here and F over here. No change. The same cluster, nothing to really merge. So for that one there, we're just going to no change. No change. So the minimum spanning tree T remains to be E1 to E5. So we need maybe another 2 iterations. Okay, let's now do the final 2 iterations. So now we got a minimum edge, and also clusters, and also the T. All right, let's now finish that. Okay, so for number 8, would you agree we should choose FG? Right? So that one there, we should choose the minimum, which would be FG, right here. Okay, right here. So that one there is going to be the weights of FG, which is 7. And let's call that E6. Okay, so now the cluster, let's see how the cluster should be merged. So let's see where these two vertices are. We got F and G, right? So we got F here and also G here. So we're going to merge G into that large cluster, right? We're just including it. So what's going to happen is we're going to do the clusters A, B, C, D, E, F, G. A, B, C, D, E, F, G. And you can see we only got one vertex left, H. Okay, and then for the T here, it's going to be everything plus E6. Okay, right here. Okay, let me just put them here. Okay, E5, and then also E6. E6. Okay, we might just need the final iterations. Okay, so E6. Okay, let's see. So for iteration number 9, okay, so we're going to choose this one here, right? The EH, which is weights 8. That could be the final one. So number 9. So the weights of EH, which will be 8. Let's call that E7. Okay. For E7 here, is going to contain E and H. So E and H merge. So now we are able to get everything. So this one here is going to be all the vertices V. Exactly V. Okay. At the same time, you can see that the T here is also going to be exactly 7 edges. Okay, this one here. So let's now just make it complete. So here we also got E7. Okay, and now that we got exactly, okay, let me just use a different color here. So now that we got exactly n minus 1 edges terminates. So now here, the cardinality of T is exactly equal to the number of vertices minus 1. So that means terminates. Okay, also very important for you to know when to terminate. Okay, of course, for that one there. For E7, I'll just use yellow right here. Okay, so what's the minimum spanning tree? You can think about this one here, this, and this. 1, 2, 3, 4, 5, 6. I agree. 7. Okay, give me 1 minute. I'll recap. Okay, so and what about these two edges? We don't need to because we already got a minimum spanning tree. All right. All right, so today we actually covered not many topics, but they are very thorough. So just make sure before the makeup lecture, you want to make sure you review about the minimum spanning tree problem and also the greedy method about the different ingredients, and look at the Dijkstra algorithm again, just to convince yourself it's really a greedy method. And you can also, now that we trace this one completely, you can also take a look at this particular Kruskal's minimum spanning tree algorithm. So this one here should not be very easy for you to follow, exactly what we just did. And try to also convince yourself why you also got all the ingredients for a greedy method. That's something I can also do when I recap in the makeup lecture. All right, so if you haven't really expressed your preference about the makeup lecture, please do so. And I'm gonna gather all the data and I'll let you know when that will be. Thank you so much. I'll see you soon.